Welcome to the Nestle Food Service Brampton Factory and McDonald's Ontario Distribution Center. This 11,148 square meter building is owned by Martin Brower of Canada Limited and houses a 7,432 square meter distribution center and hamburger bun freezer. The remaining 3,716 square meters is leased to Nestle Food Service, who own and operate the bakery. The bakery portion of the building is specifically designed, constructed, and equipped to Nestle food plant standards. Groundbreaking was in March 1989, and installation of the bakery equipment started on November 21, 1989, in the partially completed building. The Brampton factory became the official supplier of hamburger buns to McDonald's on May 6, 1990, supplying 12 million dozen hamburger buns annually to 220 McDonald's restaurants in Ontario. This is the visitor's entrance and access to the bakery offices and reception up the stairs. The use of natural light, open office concept, and light clean colors reflects well to suppliers and visitors the image of quality, service, and cleanliness promoted in this factory. The offices of the factory manager, production supervisor, quality assurance manager, senior accountant, and visitors are on the left side of hall with windows overlooking production area on the right side. Ceramic tile has been used in all high traffic areas for ease of cleaning and superior wear characteristics. The quality assurance demonstration lab is used for training, product testing, hamburger bun scoring, and product development. The boardroom is used for regular meetings and trainings with employees, customer staff training, and supplier meetings. The windows along the two factory separation walls give an excellent view of product entering and exiting the proofer and oven. A security keypad gives authorized employees direct access to their clean uniform lockers, employee telephone, stairwell to administrative offices, and main entrance to the factory process area. The men's and ladies' change rooms and washrooms are on the right, and cafeteria entrance on the left side of hall. Full-size windows running the total length of the exterior wall give the cafeteria an abundance of natural light. The colors and McDonald's restaurant motif create a clean, open, and friendly atmosphere. A built-up epoxy floor gives a durable and easy-to-maintain floor surface in the men's washroom, change room, and personal locker area. 3 individual showers with private change area, hot air electric hand and hair dryers encourage cleanliness and reflect the company interest in the employees. The ladies' change room and washroom is the same size and a mirror image of the men's. The company insistence on cleanliness, safety, and quality of food plant employees is immediately reinforced by mandatory use of this sanitary hand wash station by all employees prior to reporting to their work areas. To separate process areas from raw material receiving and storage, these automatic high-speed roll-up doors have been used at the 2 entrances to the process area from the warehouse. In addition to this, the ventilation system has been designed to keep the process area at a slightly higher pressure than all other areas in the factory. In the process area, the first 1.8 meter of wall is glazed ceramic block, topped by 1.8 meter of concrete block, followed by waterproof gypsum board up to ceiling. Other than the glazed block, all walls have been sealed and painted with food-grade epoxy paint, and all structural steel has been epoxy painted. All floors in the process area have been treated with a built-up epoxy floor system or abrasive surface acid brick tile in heavy washdown areas. An 18-inch wide vermin run is visible along all perimeter walls in process areas and warehouse. All packaging material and minor ingredients are received and stored in the warehouse. All raw material is stored in racks and off the floor. Access to sanitation storage room, garbage room, bulk liquid storage room, flour sifter room are located at the rear of the warehouse. These stairs lead to a ship's ladder and roof hatch for easy access to roof-mounted equipment. All make-up air equipment has been installed on the roof for sanitation and maintenance purposes. At full capacity, the ventilation system will change the air in the bakery 15 times per hour in summer, equivalent to 12,000 cubic meters per minute, and 5 times per hour in winter. This is the evaporative condenser for the propylene glycol chiller system used for the mixer and flour brew system. The flour silo penthouses are easily accessed for sanitation and maintenance. The Production and Quality Assurance Office houses the programmable controller that operates all the process equipment in the factory. Stewart Systems of Plano, Texas are the major supplier of equipment and control the operation of all process equipment with a Westinghouse high-performance programmable controller, nicknamed the FIFO. A compact 386 computer interfaces with a full graphics package that allows operators to call up customized graphic screens. In this way, operating parameters and formulation can be changed or monitored at any time. The system produces shift reports, enunciates alarm conditions and system malfunctions, and provides management tools such as inventory control, statistical quality control data, and production scheduling. Because the FIFO is critical to the operation, a backup or redundant system is always online. The two FIFOs constantly monitor and update each other. If a fault occurs with one, the backup automatically takes control via an electronic switch. Ladder logic changes for the FIFO are done through a separate and dedicated portable computer. A telephone modem, when connected, will allow engineers at Stewart Systems to monitor, troubleshoot, and modify the program. The process is divided into the flour and bulk liquid system, the brew yeast clean in place, or CIP system, the proofer system, the oven system, the pan system, and the product and tray handling system. Each system is supplied with a Stewart-designed main control panel located near the equipment it operates. Each control panel contains all the motor starters, variable frequency drives, and the input-output boards necessary to operate and monitor the equipment in its system. A serial interface module, or SIM, in each panel is connected by a highway cable to the FIFO panel. We will now look at the operation in detail. Located at the side of the factory are the rye melt bulk storage silos. Each hold 50,000 kilograms of hard wheat flour. The factory uses approximately 25,000 kilograms per day. A fluidizing cone and rotary airlock deposits the flour into a pressurized pneumatic conveying tube at a rate of 113 kilograms per minute. The flour then passes through a rye melt rotary inline pressurized 30-mesh sifter to remove lumps and contaminants before it is sent to one of 3 process hoppers. Overs and contaminants from the sifter are collected in the white pail for screening and inspection by quality assurance. The bulk liquid storage room houses a 30,000-liter liquid sugar tank and a 24,000-liter liquid shortening tank. The tanks are welded stainless steel construction, covered with a 20 mm PVC jacket over 76 millimeters of rigid insulation. The cone-shaped bottoms are externally heated by heat-tracing blankets, and pumps constantly circulate the liquids through the heat-traced stainless steel delivery pipes, thereby eliminating the need for in-tank mechanical agitators and heaters. Inventory is monitored by electronic liquid level transmitters tied into the main control computer, which gives a graphic representation of inventory and temperatures. A nitrogen blanket is used to protect the shortening from oxidation. An ultraviolet light treats all air entering the sugar tank, reducing risk of crystal formation. The tanks and piping are cleaned by the central CIP system. On approval by quality assurance, suppliers' liquid bulk tankers connect here for cream yeast, sugar, and shortening deliveries. All liquids pass through a dedicated inline strainer to remove contaminants before entering liquid storage tanks. All minor dry ingredients are electronically scaled here and manually put into the dry ingredient mixing tank. The ingredient required and its amount is enunciated by a visual display from the main control computer. All ingredients used are automatically deducted from inventory. The brew processing area was supplied and installed by WHE Process Technology Group. The closest tank is the dry ingredient mix tank. It is on load cells monitored by the FIFO. Tempered water, liquid sugar, and liquid yeast are automatically weighed in. The operator is now prompted to add the minor ingredients, which are verified by the system. Flour is now automatically added and blended into the slurry. A typical batch size is 4,300 kilograms, enough for 2.5 hours of production. After blending, the brew is automatically pumped over to the fermentation tank and gently agitated for 60 minutes. Glycol cooling jackets prevent the brew from exceeding 30 degrees Celsius. The mixture is now at optimum strength and consistency. To stop further yeast activity, the brew is now cooled to 5 degrees Celsius as it is automatically pumped through a cherry burl plate heat exchanger on its way to a one of two cold hold storage tanks. The tanks have a capacity of 9,500 liters each and are fitted with scraper-type agitators. Bottom and side glycol cooling jackets maintain the 50% flour brew at 5 degrees Celsius until it is needed. The bulk cream yeast system is comprised of an 18,000-liter bulk storage tank and a 9,000-liter day tank. Glycol cooling jackets maintain yeast at 2 degrees Celsius. Solid separation is minimized by propeller-type agitators in each tank. The day tank will hold enough yeast for up to 4 days production and allows time for CIP cleaning of the bulk storage tank. This panel is located beside the dry ingredient mixing tank. The Vorn digital display gives the operator information such as what part of the cycle the brew system is in, amount of ingredients added, and alarm messages if they occur. The operator can stop and start the brew formulation process from here, and also control the 3-tank CIP system. The weigh tank is on load cells and automatically weighs in the correct amount of liquid sugar, water, nutrient mix from the tank to its right, flour brew from the cold hold tank, and liquid shortening. A typical batch size is approximately 450 kilograms. After a short mixing period, this mixture, when needed, is automatically pumped over to the Peerless ACBM dough mixer. Once the weigh tank has completed transferring the flour brew mixture to the dough mixer, the correct amount of flour in the rye melt scale hopper above the mixer is added. The mixer automatically starts and mixes on slow speed, 35 RPM for 1 minute, and then switches to high speed, 70 RPM for 7.5 minutes. A photoelectric level sensor on the dough pump determines when the dough mixer bowl should tilt through 140 degrees and fold the mixed dough into the Peerless dough pump hopper. The mixer bowl is cooled with propylene glycol during the mixing cycle to prevent the dough from exceeding 25 degrees Celsius. The average dough weight is 900 kilograms. When mixer bowl is empty, it tilts back into its closed position, ready for the next batch from the weigh tank. This cycle repeats approximately every 15 minutes. Proximity sensors on either side of the mixer bowl will stop bowl movement and agitator when bakery personnel come within a 60-centimeter range. On demand, the dough pump automatically starts and stops feeding dough to the AMF dough conveyor belt system. Dough is lifted up and across to a horizontal reversing dough conveyor belt. The reversing belt transfers dough to the hoppers of 2 AMF dough dividers. Each hopper has a proximity sensor to stop dough delivery when it is full. When the hopper that dough is being fed to is full, the conveyor stops, and a knife at the end of the conveyor automatically cuts off the dough. The conveyor then reverses direction and starts to fill the other hopper. If both hoppers are full, the dough pump stops and the conveyors run for approximately 15 seconds to remove all dough in transit on the belts. Twin UHMW plastic augers in the bottom of the divider hoppers transfer dough to a Waukesha positive displacement pump. A vacuum pump is used to assist in pulling the dough into the augers and remove air voids and gas from the dough. A pressure transducer at the inlet port of the pump monitors the dough pressure. This pressure is compared to a preset and adjustments are automatically made to the twin auger's variable frequency drive to change its speed so the correct pressure is achieved. This ensures that a uniform mass of dough is discharged from the positive displacement pump. A manifold at the discharge end of the pump divides the dough into 6 pipes. A diaphragm valve fitted on each pipe allows the operator to adjust and balance the manifold so an equal flow of dough exits each valve to be sliced off by the reciprocating knife. This equipment is supplied by AMF and is their state-of-the-art dough dividing technology. There is no divider oil needed, and weight control of individual dough pieces is much more consistent and accurate than previously available technology. Each divider runs at 67 cuts per minute, or 400 buns per minute, but can be run in excess of 100 cuts per minute. The dough pieces are carried by the rounder belt through the rounder bars, which forms an approximately round dough piece. The dough pieces are coated lightly with flour as they travel down a zigzag drop chute and into the plastic intermediate proofer cups. The flour prevents the dough pieces from sticking to the cups. The intermediate proofer allows the dough pieces to relax for 2 minutes from the stresses created by the dough divider and rounder bars. The weights of the dough pieces from each machine are checked every 10 minutes on an electronic scale linked to the main computer. The operator will make minute adjustments to the diaphragm valves in order to keep weights within plus or minus 1 gram of target. A dedicated graphics screen shows up to 4 hours of current scaling history for each divider and allows the supervisor to easily monitor scaling accuracy and trends. The data is stored and statistical information is calculated and printed in a daily report. After 2 minutes in the plastic cups, the dough pieces arrive at the AMF sheeting equipment. The cups are tipped, allowing dough pieces to fall into the chutes above a Bombay gate. The gates open, dropping the dough pieces between 2 rotating 6-inch diameter sheeter rollers. Exiting the rollers, the dough pieces are flat, round, and of uniform thickness. They are then transferred into the waiting pans at the AMF Panomat pan indexer. Here you can see the pans feeding into the rear of the Panomat. The pans are made of galvanized steel and are glazed to prevent sticking and for easy removal of buns after baking. The pans are sent out for reglazing after approximately 400 cycles through the system. Pans leaving pan indexer now go through the pan shaker, which centers the individual dough pieces in the pan cup. This is essential to producing a finished bun of uniform shape and proportions. The 2 pan lines are merged into one on their way to the Stewart conveyorized proofer, where the dough will slowly rise in an environment of 43 degrees Celsius and a relative humidity of 92% for 55 minutes. A metering belt ensures that no more than 33 pans per minute can enter the proofer, and that there is a minimum space of 18 centimeters between pans. At the proofer entrance, pans are smoothly transferred to the proofer's conveyor grid magnets. Photoelectric eyes ensure that pan orientation and gap are correct. 2 magnets per grid hold the pan securely, but also allows some movement so the pan is handled gently around the many curves as it travels through the proofer. The proofer's conveyor is approximately 1,500 meters long. Air and water heated by steam heat exchangers and controlled by the FIFO maintain the correct proofer conditions. The graphics package allows the supervisor to change temperature, humidity, and proof time, as well as monitor graphically over time, temperature, and humidity. Current draw on the proofer's 5 drive motors are constantly monitored and will shut the system down if operating parameters are exceeded. Pans exiting proofer are checked by photoelectric eyes for correct pan gap and alignment, and are then smoothly transferred from the grid magnets back onto Stewart tabletop conveyor. If the product requires sesame seeds, it will automatically be sprayed with a light uniform mist of atomized water and covered with seeds as the pan passes under the Burford sprayer and seeder. The FIFO monitors all products in the system and automatically controls the seeder for the particular product being processed. In the raw material storage warehouse, a bulk storage hopper for sesame seeds is manually filled from 22-kilogram paper bags and holds approximately 10 hours of production. A perforated screen inside the hopper removes foreign material as bags are emptied. A level sensor in the Burford cedar hopper automatically controls the pneumatic conveying of seeds from the bulk storage hopper. A low-level sensor signals supervisor when bulk storage hopper needs refilling. Similar to the proofer, pans are now metered into the Stewart conveyorized natural gas oven and smoothly transferred onto the oven's grid magnet conveyor. The oven conveyor is 230 meters long, and the pans take approximately 8 minutes to travel through the oven, which operates at an average temperature of 250 degrees Celsius. Maximum oven output is 3.5 million BTUs. The oven is equipped with a forced convection air system to improve heat transfer. Air distribution pipes can be adjusted manually to ensure uniform color and bake. The supervisor through the graphics package sets oven temperature and bake time and can monitor temperature control and the condition of the 12-ribbon burners. After leaving the oven, the pans enter the Stewart depanner. The pans first pass under a row of compressed air nozzles, which serve to loosen buns from the pan cups. Then, under the depanner vacuum belt, which is fitted with small suction cups that come in contact with the buns and gently grip and raise them out of the pan cups. The buns are now released onto a wire transfer conveyor, and the empty pans continue on the conveyor beneath it. The empty pans now travel up an incline conveyor and proceed along into the Stewart recirculation tabletop conveyor, where they pass through a Baker-Mate pan cleaner, which removes buns that escape the depanner and any remaining sesame seeds. The pans take approximately 5 minutes to travel through the recirculation conveyor system, which allows them to cool for immediate reuse. At this point, the pans can either be removed from the system or, if still required, continue on around to the two Panomat machines. If the pans are not needed, they will be diverted by a vertical switch to the Stewart pan stacker and loaded in stacks onto a pan truck. The Stewart pan unstacker will automatically remove stacks of pans from the pan truck and insert individual pans onto the pan conveyor line. When the system is full of pans and on total recirculation, there are approximately 2,500 pans in the system. After the depanner, the buns are carried along a Stewart Multiflex conveyor to the Stewart Monoflex cooler. The supervisor can vary the cooling time from 23 to 35 minutes in the graphics package to achieve an internal bun temperature of approximately 35 degrees Celsius, the optimum bun slicing temperature. All overhead conveyors have been suspended from the ceiling. In the building design stage, the concrete double T roof system was chosen for it minimizes hard-to-clean dust accumulating ledges, and it also allowed threaded inserts to be cast into the concrete for supporting equipment. The 20-millimeter threaded inserts can support a dead load of 700 kilograms each. This design eliminated the need for floor support structures and the inherent traffic flow problems around them. The concrete roof has been treated with a mold-resistant sealer. At the exit of the bun cooler, the product is transferred on and off the 180-degree curve of the Stewart variable capacity accumulator. This is used to automatically provide 0 to 2 minutes of accumulation in the event of a minor disturbance without shutting down the line. The 180-degree curve extends back approximately 26 meters in 2 minutes. When the disturbance is corrected, the accumulator will retract back to its original position in about 25 minutes, thereby not overloading the packaging system. To aid in sanitation, the cooler is equipped with a metal wash cooler grid washer. Steam-heated high-pressure hot water and a high-velocity blow-off fan for drying can be turned on at the end of production and will clean the cooler conveyor in approximately 40 minutes. Upon leaving the VCA takeaway conveyor, buns now travel through the Stewart horizontal switch, which splits the flow of buns on demand to the two Stewart P77 automatic pillow pack bulk packer and bun slicers. Buns are sorted and inspected here for color and uniform shape, as they automatically enter one of 6 grouper lanes. This bun scoring board aids operators in defining correct color, height, and seed distribution. Every 10 minutes, bun weights are checked on an electronic scale linked to the computer. 4 hours of current graphical history is produced on the graphics package for the supervisor. All data is accumulated, and a report at the end of the shift prints out statistical quality control information. A group of 30 buns are released and conveyed through the bandsaw type slicer. A proximity sensor will stop the line and warn the operator of a broken slicer blade. Slice thickness is routinely checked, and bandsaw blades are replaced approximately every 8 hours. The group of sliced buns advance immediately into the film overwrap and heat sealing section. All packages are code dated. Seal temperatures can be monitored by the supervisor on the graphics package and adjusted as required. The pillow packs can process up to 27 packages of buns a minute under optimum operating conditions. The fully sealed package advances through the Goring Kerr metal detector. Contaminated packages are automatically removed from the system for quality assurance to inspect. All the plastic trays are returned to the bakery by Martin Brower and stored in the tray storage room. This room is totally isolated from the production area and also contains the Convey tray washer and dryer. All trays are washed and dried and immediately enter the tray handling system. The tray is a unique design in that it is fully nesting when not in use to maximize storage density. It will also nest in 2 positions to handle a single package of buns or a double package of buns. This is important since all buns are immediately frozen after processing, and therefore optimization of freezer space is critical. Here you see a washed and dried tray entering the Stewart tray handling system. The FIFO controls the tray washer conveyor and advances trays through the washer as the system downstream requires them. The trays leave the tray storage room and enter the process area on the lower overhead conveyor and proceed down to the Stewart pack stack tray accumulating conveyors. After passing the metal detector inspection, the packaged buns proceed into the Stewart pack stacks, where the buns are automatically placed into a clean, empty tray. Depending on product, another package of buns can be placed on top of the first. The system will handle up to 27 trays a minute for single pack trays. Loaded trays now proceed onto a metering belt, and both tray lines are metered into a single tray handling conveyor. A gate times and meters trays into the Matthews elevator conveyor, which transfers them onto the overhead tray conveyor. This was done to save space, allow for fork truck traffic, and top-down tray stacking. Trays are timed and metered into the advanced Pulver tray stacker Bombay gates. Photoelectric eyes signal when the correct amount of trays are in the stack. The full stack is then ejected onto the gravity roller conveyor. The FIFO controls the stacker and automatically adjusts stack height depending if trays are double or single packed. The stack trays are manually placed on pallets and wrapped near the top to improve stability. Palletized trays are manually recorded onto a production sheet, tagged with a production date code, and moved by fork truck into Martin Brower's 930 square meter freezer. A vestibule creates an airlock between the freezer and factory process area. The freezer is designed to take the 35°C buns down to a core temperature of -23°C in 8 hours. The freezer, when full, will hold up to 53,000 trays, approximately 3 days production requirements for McDonald's. This allows factory personnel weekends off and most holiday weekends. Gravity roller racking is used in the freezer to assure first in, first out stock rotation at the other end of the racks by Martin Brower, who handle and distribute the buns from this point on. A computerized preventative maintenance program is used to schedule work and monitor spare parts inventory. The maintenance shop houses a welding area, lathe, drill press, milling machine, grinder, and mechanics workbenches. The spare parts storage is located above the maintenance shop and houses $300,000 worth of inventory. Since most of the process equipment is very specialized, it is important that critical components are available in-house to minimize unscheduled downtime. The mechanical room houses a Cleaver Brooks 80 kilowatt natural gas-fired boiler, two 100 kilowatt air-cooled air screw style air compressors, only one is required to operate the bakery, and a refrigerated air dryer and a desiccant air dryer for flour silo pneumatic controls. The 12 kilopascal steam distribution system returns all condensate to the boiler. No live steam is used in the process. Steam is used for the proofer conditioner, 1,500-liter process hot water tank, CIP heat exchanger, and tray washer. The factory electrical distribution room provides up to 2,000 amps at 575 volts, three-phase, 60 cycles. The glycol refrigeration room houses two 30-kilowatt Simco Freon 22 compressors and a 5,500-liter insulated glycol storage tank for a total of 175 kilowatts of refrigeration. This room is located above the production office so as to be as close as possible to the dough mixer and the flour brew processing system. The 30% propylene glycol and water mixture is used for refrigeration of the brew system tanks, heat exchanger, and dough mixer, and is maintained at -2 degrees Celsius. Access to the feed chute of the garbage compactor is from the garbage room. All process drains terminate at a 1,000-liter capacity grease interceptor in the garbage room floor. It is pumped out by tanker truck through this small access door. The garbage room also houses the central vacuum system centrifugal exhauster and air separator filter. It is connected by mild steel tubing to pickup points at bottom and top of all structural steel columns and halfway along all main support beams in the factory. The system will handle up to 4 operators at a time. This is the most modern, state-of-the-art bakery supplying McDonald's in North America. The factory manager, a certified baker, is supported by an administrative assistant, a factory accountant, quality assurance manager and technician, a sanitation manager, production supervisor, afternoon shift supervisor, and factory engineer. The factory operates with 10 hourly paid equipment operators and 2 mechanics per production shift. The midnight shift is used for sanitation and employs 6 hourly paid sanitation department personnel and 1 preventative maintenance mechanic. The factory currently runs 2 8-hour production shifts on a 5-day schedule and has successfully met all McDonald's requirements since startup in May 1990.